Okay. So it's a pleasure to have Dr. Daskalopoulos today.
Right, so I would like to thank Alice, Matt, and Luis for organizing this very nice workshop. So I'm going to change a little bit the tone, and from elliptic, I'll do parabolic today. And what I would like to discuss is a classification result for ancient solutions of the curve shortening flow and the Ricci flow on surfaces. So I'll explain what an ancient solution is for those who don't know. All right. So we will consider, so in the first part, which is kind of the easy version of this, so we decided to do this problem just because we wanted to do this. But I think it's interesting anyway. So we're going to consider an ancient family of closed embedded curves, convex embedded curves, which evolved by the curve shortening flow. And what does ancient mean? Ancient means that they exist all the way for time, all the way from minus infinity up to capital T. Can I the laser is to point or not?
There's a laser pointer on.
Ah, that's different. Is this one? No.
No, it's the one on the side.
Sorry, it's not this. I cannot use this laser, no?
I don't know if it works properly.
Ah, that works, that works.
Okay.
Okay, thank you. Okay, so in the first case, we're going to prove that this family of ancient solutions is either a family of contracting circles, which is like the obvious one, or it's a family of, as we call, evolving angenate ovals. And we're going to see that the contracted circles is what we call type 1, and the evolving angenate ovals is what we call type 2. I apologize, my PDF file has small letters. I hope you can read. So in the case of the Ricci flow on surfaces, so it's the 2D Ricci flow, we're going to consider an ancient solution again of the Ricci flow on a compact surface that again exists all the way from minus infinity and has to become singular capital T. That's a theorem. We're going to prove that this metric, evolving metric, again is either a family of contracting spheres, which is like the obvious type 1 solution, or the so-called Rosenau solutions, which are type 2. And I'll explain. And this, whatever I'll talk today, is joint work with my colleagues, Richard Hamilton and Natasha Sesson.
Can I ask about the convexity assumption in the first theorem?
I'll get back to you at the end.
Okay.
Yes. You're very much ahead this time. Okay. I'll have a slide. I'll put a slide at the end, and I'll discuss it a little bit. Okay, so let me review fast about, again, our motivation was to do the Ricci flow on surfaces, and we had some problems, so we thought to do this what looked a little simpler, and you're going to see that this is much simpler than the other one. Okay, so let me remind you what is the curve shortening flow. You consider a curve, a family of curve gamma t, which move with a speed which is proportional to the curvature of the curve. And it's right in this case, we're going to consider only for the beginning closed convex curve, so they're going to move inward. And it's well known that this equation is actually the heat equation on the curve gamma t with the induced metric. And it's a known result of Michael Gates and Richard Hamilton that if you start with something convex, then you start with a convex curve, then the flow shrinks this convex curve to a point, and the more it goes closer to a point, the more it becomes round. So you're going to see at the limit, after some renormalization, you see a circle. And actually, Matt Grayson extended this result on any embedded curve in R2, and actually it's a beautiful result most of you are familiar with. Even if you start with a very complicated embedded curve, of course non-convex, it will not develop any singularity before it becomes strictly convex. And people that they are familiar with the mean curvature flow, which is the generalization of the curve shortening flow in higher dimensions, they know very well that this doesn't work in higher dimensions. Okay, so we're going to assume for the remaining of this part of the talk that we have an ancient convex solution which is defined up to a singular time t, and I'm going to take this t for simplicity to be 0. So we know that there is going to be some singular time. There's no question. It's not going to go all the way to plus infinity. Okay, so in the case that you have actually a convex curve, the whole evolution of the curve is captured by the evolution of the curvature. So we can just forget like what's happening like on the curve itself, just study the evolution of the curvature, and that's equivalent. And in terms, the evolution of the curvature in terms of arc length takes this very simpler form. So it's like a semi-linear heat equation. That's well known. Now, if S is the arc length, now if you want something that it's independent on the curve, then you can parameterize it by the angle theta, which is between the tangent vector of the curve and a fixed axis, let's say the x-axis. Then you end up with a very nice, again, PDE, which is like of a porous medium type of equation, which is kappa sub t is kappa square theta theta plus kappa cube. And for those of us who are familiar with the porous medium equation, it always makes sense to introduce a pressure function which has a better properties. So instead of taking this kappa square here, we make it kappa. So then the pressure function, which is kappa square, evolves by this nice equation. So it's Pt is P theta, etc. And now we say that our family of evolving curves is type 1. Now it goes, we're going to look what happens now, not what as t approaches the singular time, because that's well known, but as t approaches minus infinity. And it's type 1 if the supremum of the absolute value of t is negative in our case, multiplied by the pressure is less than infinity. Otherwise, the curve is called type 2. Sorry. Okay, so now we have two examples of ancient solutions, the type 1 of type 1 and of type 2. And actually, it would turn out that if you restrict, at least in the convex case, these are the only ones. So, of course, the one is the contracting circle. The pressure is constant. In theta, it just depends on time. And the other one, and that you can see that this is like type 1. And the other one were observed, they were constructed by Enginen, and they have this form. The p actually, what is it? It's just a function of t minus just a function of theta. So it has this form, a function of t minus a function of theta, the pressure. And the theorem is just that you have only these two. And the one is type 1, and the other one is type 2. Okay, so let me just tell you how we prove this, and it's simple. It's not difficult. Okay, so I remind you that we're going to work with the pressure, which is the square of the curvature, and this captures, again, the whole behavior of the equation and satisfies this equation. Now, it's a well-known inequality, the so-called Aronson-Benellan inequality for the porous medium equation, which says that actually on P sub t, on an ancient solution, P sub t has to be bigger than or equal to 0. Okay, so this means that we have this elliptic inequality all the time, and actually this means that this limit exists and we have no problem. Now, the only problem is that this limit may become 0 at some points, which means that this equation becomes degenerate and creates a little bit of problem. But again, in this case, we're going to see that this is not a big problem. Okay, now, so the proposition is the first proposition. The first proposition is that the backward limit p tilde, it has the form. So the backward limit is well defined, and you would like to show that somehow has the form that we want, which is like the backward limit of what happens either when lambda equals 0, which is the case of the contracting circle, or lambda positive, which is what is of the angular ovals. I mean, notice that these angular ovals, the same thing in the Ricci flow, are not really soliton or self-similar solutions. So they cannot be captured by a monotonicity formula or something like that. So we have to classify them a little bit differently.
At minus infinity becomes two lines?
At times infinity?
At minus infinity, the ovals become
It's this.
lines?
Yes, exactly. It's like, okay, at minus infinity, it's just 2 Gram Reapers. You know, Gram Reapers are it's like 2 self-similar solutions, right? So as we shrink to minus infinity, this angular ovals, the way you picture them, is like 2 the Gram Reapers are the kind of cigar solutions for the sort of separating for the curve. So
Asymptotically become like two parallel lines.
exactly.
Are the parallel lines at infinite distance from each other or finite?
Finite distance from each other. Okay. Okay. All right. So how do we prove this? I think. Let me see. I think I skipped the slides. I'm sorry. Oh, here we are. Okay. So how do we prove the proposition? So we would like to say that as t approaches minus infinity, right? The p sub t, the pressure, the time goes to 0. The p sub t, the time derivative goes to 0. Therefore, the limit, which we know that it exists, at least in some weak pointwise sense, satisfies our relatively nice PDE. And for this, we introduce a Lyapunov function, which is j of p, the integral from 0 to pi, etc. And a direct computation actually shows that the ddt of this Lyapunov function is a monotone quantity, and because you have that at all time p sub t is bigger than or equal to 0, you can integrate by parts and actually show that the pressure is always the Lyapunov function is always bounded between 2 constants. The one happens to be 0. Right? So since this has to happen all the way to minus infinity, this forces that p sub t, at least in some weak sense, goes to 0. Otherwise, you're not going to have something integrable because j of p is bounded. All right, that's like a classical thing to show that something converges. So in some weak sense, then, we know that p sub t goes to 0 weakly. And of course, since p tilde satisfies, so the limit satisfies this PDE, right? You obviously, like for very standard elliptic estimates, whenever p tilde is bigger than 0, you have like very nice and smooth convergence. So the only problems is just to ask yourself where p tilde becomes 0. And we know that p tilde in our example gets to 0 at exactly 2 points, so that's what we want to show. Okay, so actually by, so now I think I'm, okay. Now, so using a priori estimates actually on our elliptic inequality or the parabolic, we can actually prove that p converges to p tilde in C1 1/2. But we don't have the better convergence because we have a degenerate equation. Okay, so we would like, now to solve the steady state equation and find that p tilde has the right form. And we would like in particular to say that p tilde vanishes in just 2 points. But let's first prove that p tilde vanishes at most somehow n points. And actually not exactly, because okay, it could be that it vanishes at 2 points and all the interval in between. So the first thing we show is that if p tilde of a equals p tilde of b equals 0, and p tilde, right, and p tilde is just not 0 in between, right, this interval, then this distance has to be big enough. And how do we prove it? Okay, it's like by a Poincaré type inequality on the one side and by integrating the equation on the one side. It's very, very easy. So by integrating this equation, you just, on the one side, you just have that this 3/4 p theta square is the integral of p squared on this particular interval. And by this Wirtinger's inequality, some sort of Poincaré inequality, tells you that if b minus a is less than or equal than mp, then this is less than or equal than mu p is less than or equal than mu square and this integral, which bounds from below mu. And once you know that you have only finite many possible zero, you can integrate your equation between two zeros and easily actually then rule out the other cases and actually show that p tilde is of the form you want. Right? So you can just prove that you have a p tilde. So you have classified then the possible backward limits, and you have that either p tilde is 0 or p tilde is what you want. And now you would like to say that this forces that your p is what one of the two solutions. Right? And so we would like to use now this to classify all the ancient solutions. And for this, we introduce a new monotone quantity. So you take alpha to be p sub theta, right? And you observe actually that when you differentiate in theta, the equation becomes actually simpler. And alpha satisfies this very simple equation. Alpha sub t is p, and the rest is just almost like the heat equation. So then you can introduce this functional I sub alpha, which is alpha theta squared minus 4 alpha squared d theta, and you get lucky, and this is like very nice. So you get that this I quantity is monotone, right? Is monotone in time. So if you can so what do you want to conclude actually? You would like to conclude that I is identically equal to 0. Because if I is identically equal to 0, this will imply that somehow you have, right? If this is identically equal to 0, then everything will be here identically equal to 0. And then you're going to actually get, then in particular, a sub t will be identically equal to 0. So a theta theta plus 4a will be identically equal to 0, which will force p sub theta to be of the form a sub t cosine 2 theta plus b of t sine 2 theta, and by integrating, you're going to get what you want. So the only thing you need to justify then is that this monotone quantity becomes 0 at the two ends, at 0 and at minus infinity. And this follows really from what we know already, from what I described, right? Because we know exactly what the limits are, and we have pretty good estimates, so we can pass to the limit as you go to minus infinity. Now, this requires a little bit of work. Here we know, on the other hand, what do we know? We know that as t goes to 0, everything becomes like a circle. So if it becomes like a circle, you expect this to be true, and you have to work a little bit harder to prove it, actually, because you need some better asymptotics, but you prove it. So once you know that these two are 0, as I said, I is identical to 0, p theta has the right form, therefore p has the right form. And that finishes the story. Okay? And now, you may ask whether convexity is necessary. And we don't know actually that it's necessary or not. Engenet claims that he can construct solutions, like kind of spiral type solutions, that they go all the way to minus infinity and right, therefore are not in our case. They don't belong in our type of solutions. They're very different. But actually, I don't know. I'm not convinced of that. I mean, because this is not rigorous. So I'm not convinced. Yes, unbounded all the way. And but when we try to work it out ourselves, so we thought that you cannot do it. So we haven't really answered this question now, right? Because the problem is that if you have something which is non-convex, then your curved shortening flow is not captured by this very nice porous medium type of equation. Because yes, right, this porous medium type of equation has only those solutions, but the ones I told you, I mean, like convex or not. But the problem is that, because you have like nice, the problem is that this is not, for something which is not convex, you cannot write, this is not, the two things are not equivalent. But anyway, nevertheless, what you can show is that actually, right, so the question is, are all ancient solutions convex, for example, right? Because if they're convex, then they follow. And it's what we prove is like, if the total curvature, right, is bounded, and the curvature itself, right, it's bounded all the way to minus infinity, then we can actually show that an ancient solution is convex. But the general case, we don't know, and it will be interesting to find out. Just going to have some. All right. Okay, so for the remaining of my time, I'm going to discuss now the Ricci flow on a compact surface and try to classify the ancient solutions. So let me remind you what is the Ricci flow. You have a metric. In our case, it's a metric on R2, but on any a metric two-dimensional on a two-dimensional surface. But in general, you have a metric on an n-dimensional surface, and you evolve the metric by minus twice the Ricci tensor. And we can, in our case, we will consider like a metric on a compact surface. And we'll consider that our metric is, our solution is ancient again, so it comes all the way to minus infinity up to time capital T and becomes singular at time t. Of course, it's a well-known old result of Ben Chao and later of Richard Hamilton that, right, everything, any evolving Ricci flow on a compact surface will become singular in finite time. And after renormalization in the two-dimensional case is easy, it becomes spherical. So we know that at time capital T, you see contracting spheres at a very small scale. So the question is, what are the possible ancient solutions of this 2D Ricci flow? Okay, so analogously with the curve shortening flow, we define what is a type 1 solution. Again, a type 1 solution is type 1 if the limb sup of the absolute value of t, now we're taking t negative, and multiplied by the maximum of the curvature at time t, all the way to t goes to minus infinity is finite. And like when you have like the contracting sphere, r is 1 over absolute value of t, more or less behaves, so this is exactly a constant on the contracting spheres. And it's a solution which is not of type 1 is called type 2. So this, on a type 2 solution, this is infinite. Okay, and it's well known that the only ancient type 1 solution on a compact surface are the contracting spheres. So the question now is to classify the ancient type 2 solutions. But anyway, we're going to classify all of them together.
In this theorem of Shaw and Hamilton, you need convexity of initial conditions?
No, absolutely not.
There's no initial conditions, there is just
There is no initial condition.
okay, so
No,
Implicitly, in comparison with the curve shortening, you are assuming that the curves in the previous problem will be bounded for all past time. Right?
No, I'm not assuming. What you?
I mean, sort of, if you make a comparison of this with the other result, the compactness assumption here is like
Exactly.
which will not be the example of Angener. The countergrammar will be a spiral which will be unbounded for all time.
I mean, yeah. So you're saying the width somehow, right, is bound. The width of the spiral is bound. Yeah. But here, I mean, these things. I mean, the spheres, right? They become unbounded. Like the width of the sphere becomes unbounded.
Yeah,
Now the cigar.
The hypothesis is that for all past times, for the curve shortening, would be to assume that the curve in all past times is bounded.
I mean, it goes all the way to minus. Okay, we will talk about it now. Yeah. So, okay, so our goal is to classify now the ancient solutions. Okay, I'm going to make sure that I don't jump. Okay. Okay, now let's write down some equations that we're going to work on. So we consider now an ancient solution, an ancient metric, and we know, let's assume that it becomes singular. From now on, we're going to assume that it becomes singular at time 0, right? So nothing happens for t positive, everything happens for t negative. Now we know that as t approaches 0, from the theorem of Hamilton, you contract to a sphere, right? So you can parameterize, right? So we choose a parameterization, right, of the limiting. So at time t equals 0, you see a sphere, so we parameterize our flow with this limiting sphere. And so therefore, you write somehow your G now as U multiplied by the metric on this limiting sphere, which is like the spherical metric, and it's just this. And so then we have a very nice equation on S2. So this Laplacian now is the Laplace-Bertrami operator on S2, so it's not on the evolving metric here. So this somehow in this, because you're in 2 dimensions, you can write G as a conformally somehow equivalent to the standard metric on S2. In higher dimensions, of course, you don't do that. You cannot do this. Okay, so then your U, your function U, your evolving like conformal factor, satisfies on the sphere this logarithmic fast diffusion equation, du dt equals Laplacian of log of U minus 2. And now we're going to be working on the sphere, on the cylinder, and on the plane, because sometimes it's easier to work on the sphere, sometimes it's easier to work on the cylinder, etc. But for the time, this delta is on the sphere. And again, because you have a porous medium type of equation, we introduce the pressure function, which in our case, because we have fast diffusion now, is the pressure is U inverse. And now the pressure satisfies a very similar equation to what we had before. The only difference is numbers, but the equation is very similar. So dv dt is v Laplacian of v minus grad v squared plus 2v squared. So I'm going to more or less work with the pressure, but sometimes I'm going to also remind you what is a conformal factor. And type 1 solution, now what are the 2 examples of ancient solutions? All right, the easy one is the example of the contracting spheres. Now the type 2 solution was discovered by Philip Rosenau a while ago. He had no idea that that was the Ricci flow, and so he found that the solution is of this form. So your pressure function, so he looks for pressure functions which are of the form a function of time minus another function of time sine squared psi, okay, multiplied by a function of psi. These are radial solutions, by the way. They are independent of theta. And for any constant mu, don't think that we have something negative here, because the cotangent hyperbola is negative. All right, so these are 2 solutions. And how does this look like? Okay, these are like contracting spheres. Now the Rosenau solutions are it's like 2 cigars, right, which are the soliton solutions, as you go to minus infinity, 2 cigars moving apart from their glued together somehow. And these are not solitons, okay? Everybody that has worked on Ricci flow. Okay, if you're going to minus infinity, they look like that, right? So somehow, right, it's like 1 cigar and another cigar moving this way. Okay?
They're expanding.
They're moving away from each other. What?
Looks more like just one expanding cigar.
No, I mean, because they use they use this cigar. You're right. You're absolutely right. But they have already used a cigar, so I cannot use cigar. Okay. All right. So so again, right, what is again difficult in this case, so for people that have worked on the Ricci flow, they know like how important is like a solution to be a soliton, and especially when you want to capture the solution, because then you have nice equation, the nice the soliton is is captured from very nice equations that they vanish, and you can use a monotonicity formulas, entropy, etc. to capture. But we have no hope with this now because our solutions are, our Rosenau solutions are no. Okay, so what is the theorem? I told you already, is that the only ancient solutions on a compact surface are the contracting spheres and the Rosenau solutions, and of course you have a parameter on the Rosenau solutions. Okay, let me just give you the sketch of proof. Now the sketch of proof is a little bit similar to what we did before, but it's just much more complicated. Okay, so the first thing we show again, we do have a monotonicity. We show that the backward limit as t approaches minus infinity exists, and we need to work hard, a little hard, not too hard, but hard work enough to establish C1 alpha estimates for any alpha less than 1. Unfortunately, you cannot do anything better because your equation gets bad, at least at these two tips of the cigars. Okay, now, so you know that your limit exists, and you want to show that your backward limit again satisfies is a steady state, and again you introduce a suitable Lyapunov functional to show that your V tilde, your limit, satisfies the steady state equation. Okay, now the hard part, all right, I mean this is not so difficult. The hard part is now is to classify the solutions. Okay, because remember when we were doing the curve shortening flow, it was very easy to show actually you only have 2 zeros. Now you want to show that V tilde has at most 2 zeros unless V tilde is identically equal to 0. And that's much harder because we don't have anything like all this inequality, like Wirtinger's like inequality, etc. We have to do something else, and I'll explain what. So the first thing you show that it has V tilde has at most 2 zeros, and these 2 zeros are these tips of the cigar, and this is where like your estimates somehow fail, like everything like goes bad. And once you know that you have only 2 zeros, you can actually do like a simple conformal change, and up to this conformal change so that your limiting V tilde steady state is like what you want, right? Is that, so in cylindrical coordinates means that it's a constant. In these spherical coordinates, right, in sphere is c cosine squared psi. But if you just, because that looks more and more like a cylinder, so of course, if you stay in the middle, you're just going to see a constant, and that's what it says. Of course, this doesn't capture what really happens at the two ends where you see the cigars. Okay, and now we know, therefore, that V tilde is c cosine squared psi, where either c is identically equal to 0 or c is positive. And now we first have to deal with a case where c is equal to 0. Then your backward limit, therefore, is identically equal to 0. And at the beginning, actually, we really didn't pay any attention to this because, okay, we say obviously that is going to be the spheres. But actually, when we wanted to prove that, we could not. And it takes something to do that. So I'll show you how you do this. And finally, when c is positive, you want to show when your backward limit is this with this c positive, you want actually to show that you get the Rosenau, and you go in 2 steps. You show first that all ancient solutions with c positive are radially symmetric, and all radially symmetric solutions are the Rosenau solutions. And okay, what makes this problem a little bit difficult is because your equation is conformally invariant. So you always have this conformal, right? Everything is up to a conformal invariance. So you have to somehow fix right? You always have this like, okay, your classification modulo like a conformal change. And you have to decide what is this conformal change that's going to give you the right classification. Okay. All right, so the first thing is to show that your backward limit satisfies the steady state equation. So let me remind you, your metric is a conformal factor u, right? It's a metric on S2. This is the standard metric on the sphere. and your pressure, which is U inverse, satisfies this PD. Now, what is this V sub t? V sub t is the scalar curvature multiplied by V. And you know that if you have a non-flat metric on an ancient solution, the scalar curvature is strictly positive. So you have a very nice inequality. You know that V sub t is positive, therefore your limit exists. So there's no problem to show that the backward limit exists and is bounded, and that you have to work a little bit to show actually that in C1 alpha for every alpha less than 1. Now, unfortunately, you cannot get better. You're going to see that for our purposes, we would love to have here C2 or C11. And you cannot really get better, or C2, let's say. The problem is that at these 2 points where V is 0, your equation becomes R is discontinuous. So the PD cannot give you any better regularity, although you do actually have better regularity at the end because you have classified your solution. Okay, now you want to introduce a Lyapunov functional which will give you the convergence to the steady state. And this is not, so we introduce this Lyapunov function. Now this is not your standard Lyapunov function. This is not like the entropy for the Ricci flow, because the entropy would have had a V square here, because it's like the gradient of log of U square. But if you put the V square, which will give you kind of a better ddt here, on the Rosenau, it's minus infinity at minus infinity. So with the V squared does not work, but you get lucky. Actually, it works with the V, because d dt of j of t, you get this first term, which is okay how it's supposed to be, and then you have the second term, which fortunately for us V sub t is positive, so you still have something negative. So your Lyapunov functional, you can also show by integrating by parts the equation that your Lyapunov functional is always bounded between two constants, and therefore, right, this is going to force, right, the fact that this is integral j of t is bounded, that forces all these to go to 0, at least along some sequences, and you can actually show that your limit satisfies your steady state equation in some weak sense. Okay? All right, so now we would like to classify the backward limits. So the theorem is that there exists a conformal change of S2 in which the limit, right, the backward limit, and notice that our equation is conformally invariant, so we can do any conformal change, the equation is not going to change. And our limit then is what we would like, c cosine squared psi. In cylindrical coordinates means that this will be constant for c bigger than or equal to 0. And the convergence is C1 alpha on S2, what we knew, and of course it's C infinity away from the poles, because once you know that your steady state is non-zero, right, you have very good control of your PD. Okay, and so the main step, as before on the curve shortening flow, is to show that either V tilde is 0 or V tilde has at most 2 zeros. But of course now it's a little bit harder to show it. Okay, so let's recall some properties and see what's happening. So you look at R tilde, which is the limit as t approaches minus infinity of R. Now this limit, honest limit, exists because R sub t is non-negative, and that follows from the Harnack estimate on the differentiable Harnack estimate that you have on R, and because you have an ancient solution. So you have a monotonicity of your curvature, and you know that R tilde is always bigger than or equal to 0. This is their limit. And actually, you know that R tilde is 0, because R tilde, it comes, right, you have shown like right here, in particular, you can prove that V sub t over V in absolute, like it's positive, the absolute value, I mean Vt squared over V squared goes to 0 weakly, and this is exactly what is your R. Okay, so So you have these two, and then you have Gauss-Bonnet theorem, which tells you actually that the total curvature, U is your conformal metric, conformal factor, your total curvature is always 2 pi. Okay? So, okay, you get weakly going to 0, but then you have some points or some regions or whatever where you get something that is not 0. And, right, and of course the main difficulty, as I said before, is that R tilde is discontinuous at the point where R tilde is bigger than 0. Okay. And so, right, so at the points where R tilde is continuous, you have nice control. So you only need to worry about the points or regions, whatever, you don't know a priori, that R tilde is bigger than 0. Okay, all right, so we would like to prove the claim, so we would like to prove that R tilde or U goes to infinity, V vanishes, R tilde becomes 0 at most, right, finite many points, which are actually at most 2 points. And this R tilde exists in a nonal sense because it comes from a monotone limit. Okay, so let's say U is our conformal factor, which satisfies this nice PDE. I think this is minus, I made a mistake, this is minus RU. When it's written in terms of V is plus, but this is minus RU. And you define the set where R tilde is bigger than 0. So first, because you have that the total curvature is finite, using a covering argument, you actually show that Z has finite many points. And now, once you know that your Z has finite many points, then you actually show that what happens is that if you're away from these points, P1, Pn, then you can make the integral in neighborhoods, like in sets, small sets, which are centered, let's say small balls on the sphere, which are centered at points which are away from these points, you can make these integrals uniformly small. Once you make this interval uniformly small, you can do a priori estimates in this PDE. This was like similar estimates were done by Brazis and Merrill, and you can actually show that once this is like small sets, then on those sets you have a bound on the supremum of U, and it's uniformly on time. So, right, so then you prove actually that there exist finite many points away from which, so you have a compact set, you can bound the supremum of U uniformly in time. And remember, the pressure that we are trying to classify is U inverse. So bounding the supremum of U from above, you bound the supremum of U means that you bound V tilde. So then you know that you only have like finite many trouble points, and you only want to have 2. So what you do a blow-up argument around these points, and actually when you blow up around, let's say, P1, then you actually end up with an NCN, actually it's like an eternal solution that lives from minus infinity to infinity of the Ricci flow. This is like a complete non-compact solution, and we have classified this in an earlier paper with Natasha Sesum, and we know that these are the cigars, those stones. Right? So you know that very, very close, if you focus around each of these points, you see a cigar. But then this quantity Ru is invariant under your dilation, your blow up, and on the cigar, Ru is 4 pi. So you cannot have more than 2, and then you're done. So this implies that, therefore, you have at most 2 zeros, and V tilde has at most 2 zeros. Okay, so then we would like now to show that V tilde is a solution of this PDE. I'm not going to write it right again because it doesn't really matter, and it has only 2 zeros. All right, and now it's easy, like you can just right? Now you want to fix your conformal change of coordinates. So you know that you have these 2 zeros somewhere on the sphere. Now you can just change, you can perform a conformal change of coordinates on S2, which brings these 2 possible zeros, right, on the 2 poles, S and north and south pole. And then the easiest thing to do is now to project everything from, using the Mercator's projection, from S2 minus this 2 to the cylinder. Then, so in terms, if you want to write in terms of coordinates, now if x is the coordinate along the cylinder, then w of x theta t is just v psi theta t cosine hyperbola square x. And now it turns out that w satisfies a nice equation, Laplacian log of w equals 0 in cylindrical coordinates. And you can classify, of course, very easily. I have it there, sorry. I didn't see. Your w, right, you can classify, of course, this has many more solutions at the constants, but using our geometric considerations, you deduce that w is a constant. So that's easy. Once you know that you have 2 zeros, then you're not a problem. You see, if you had more zeros, then of course, or like you didn't, then you have no idea how to classify those solutions. Okay, so now we know what the backward limits are, right? Exactly, are like in cylindrical coordinates are constants, right? So then you would like to say, right, let's say that this constant is 0, I see the spheres. Okay, now, so if this limit is v tilde, which is 1 over u, where u is your conformal factor, is 0, then you want to say you see the spheres, where u obviously has limit 0. Okay, now for this, actually, we thought we could do it with PDE, but we didn't find a way, so we used a little bit of geometry. So we use this isoperimetric, because we want to show like that you end up with a sphere, right? It makes sense to consider the isoperimetric ratio, which, has this nice property, I'll explain in a second, that, right, characterizes which, right, two-dimensional surfaces are spheres. So what is this isoperimetric ratio, right? You take any surface and you take a closed curve on your surface, and this closed curve divides of some length, divides your surface into two regions of areas A1 and A2. And you can view, now we have our surface, which is like S2, but not with the standard metric. So we can view our surface to be like the sphere, but where the metric is not the standard metric, it's our evolving metric. Okay, so then we can define the isoperimetric ratio to be 1 over 4 pi, the infimum over all these curves or possible x, the length square of the curve 1 over A1, 1 over A2. And note, because of Gauss-Bonnet, A1 plus A2 is always 8 pi t, 8 pi t. Okay, now it is well known that, okay, I is identically equal to 1 if and only if we have the surface is the sphere, otherwise I sub t is always less than or equal to 1. And a while ago, Hamilton has computed actually the evolution of I prime and has found that I primes, right, satisfies in an equality which in our case where A1 plus A2 is 8 pi t gives us this inequality. So this I prime satisfies this nice ODE differential inequality, which forces, of course, that if I sub t is less than 1 at some point t naught, then you have this fall off. And somehow, you remember, this is like 1 over the area. So it's like what you expect to have the sphere. So you want to show that because you have this fall off, right, then you derive somehow contradiction, okay, because you want eventually to end up with this. And what we find, we have to work a little bit to find actually this, but I don't have the time to show you. You find that actually there exists, because of this fall off, you can find a sequence of times that goes to minus infinity and some curves on S2 which have the two properties. If this curve, the length of this curve is measured on the standard spherical metric, is bounded from below, but and on the other hand, again the length on our evolving metric, right, it's bounded from above. And this follows from this, but of course you have to work actually a lot to be able, not a lot, but you have to work somehow to get these two. And so that obviously contradicts the fact, because what is the length in this metric is somehow an integral over u, the conformal factor, multiplied by the length of this. So you integrate over this, you integrate u over a curve which has not zero length, all right, bounded from below length on S2. And that's a contradiction to the fact that u goes to plus infinity all the way, right, uniformly. U goes to plus infinity uniformly, because we have shown that. And so that finishes the proof. And now let's go back. So we have now we know that if this c constant that we see at the steady state all the way to minus infinity is equal to 0, we see our spheres, so that we only have to worry when c is positive. And now, first I'm going to assume now, so therefore now we want to classify all solutions which have this as steady states, and so that these are our Rosenau solutions. And we will go step by step. Let's assume first that V is a radial ancient solution. Radial means that V is independent of the theta that I had before, depends only on psi. Psi goes between minus pi halves and pi halves. Right? So we have we know that we have this limit, and we want actually to show that V is of this form. If you remember, when we did the curve shortening flow, we were very lucky, because the evolution equation, when we differentiating V with respect to, let's say, psi, it was not psi before, satisfied a nice PDE, and then we were able to find a nice monotonicity formula. Now, nothing works as nicely here, and the easiest way to do this is now project again, and you take S2 minus the pole. One is like the center of symmetry of your psi, let's say plus half. The other one is minus pi halves. You take these two poles, psi equals plus minus halves, and you project S2 on the cylinder, where the corresponding metric on the cylinder solves this very nice, very simple PDE. Still, we cannot find a nice monotonicity formula for this. So what you want to show that an ancient solution of this PDE with this, where as W goes to minus infinity, you see a constant here, because on cylindrical coordinates this goes away, is of this form. Because Rosenau solution in cylindrical coordinates is of this form. And of course, now what we do is we set Q to be WXX minus 4W. And if you can show, you see that on the Rosenau solution, this is just a function of time. So you want to take F to be QX squared, and you actually find that this QX squared has a fairly nice evolution equation, and you're able to show actually that F sub t is less than equal than WFXX. Satisfied is very nice. And now you know that the limit as t approaches minus infinity of F is 0, but here you have a lot of problems, because now your set is non-compact, and you don't have a nice control of your derivative estimates all the way to minus infinity, because your PDE allows you only to do C1 alpha estimate. So to apply the maximum principle here, to justify it, you need to construct very careful barriers, but I'll omit the details. Applying because you go all the way to minus infinity also, so you have to worry. But you can still do it, and the maximum principle will guarantee that F is identically equal to 0, which means that Q is just a function of time, and which means that after solving and putting back in the equation, it gives you that it's the Rosenau solution. And my last slide is to show how solutions are radial. And now for this one, it's easier to express everything on R2. So you have a metric on S2, you can project via stereographic projection and express your metric as a conformal factor U bar, multiply the metric on R2. And then U bar satisfies this very nice equation on R2 now. And let's say that U bar, express U bar in polar coordinates R and theta on R2, and you actually show that the integral over R2 of this U bar theta, actually turns out that U bar theta satisfies a nice PDE, and you saw that this I sub t is decreasing in time. The total, the absolute value of u sub theta is decreasing in time, and moreover, this goes to 0 because at the limit you see a radial solution. Therefore, since we also have that I sub t is bigger than or equal to 0, that forces I sub t to be identically equal to 0, which forces u bar to be independently of theta, therefore radial. And again, in this and all the arguments, one of the main difficulties is the lack of good a priori estimates all the way up to the poles of where the singularity is. So you have to be careful and make these statements rigorous. And let me just, to finish, pose some open problems. We still do not know whether there are any equivalent of the Rosenau solutions. Of course, I'm not saying they're the same, but like non-soliton solutions, ancient solutions in a 3D Ricci flow, and what to classify them. Now, if you want to somehow look what happens in the higher dimensional case of what I described, is not so much the Ricci flow, but it's more the Yamabe flow, because what I described is just also kind of the two-dimensional Yamabe flow. And it was observed by J.R. King and Simon Brundle that there exists, you can find Rosenau type ancient solutions. And the question is, are there any other solutions? And we have a little bit of suspect that in this case you have many more other solutions, and which, of course, to classify them will make much more difficult problem. And I asked the experts, and they have no idea what happens, for example, with ancient solutions of the mean curvature flow, even in the convex case. We do think there are quite a few ancient solutions convex ancient solutions in the case of the mean curvature flow. For example, the corresponding of the Angenette ovals, and I think we can prove their existence, but they don't have a nice form. You cannot write them explicitly, which means classifying them will make a much more difficult problem. So I'll just finish this. Thank you.